Imagine a planet so mysterious that even the greatest minds in science are left baffled by its secrets. A world where the skies shimmer in a haunting blue hue. Its entire body tilts almost sideways as it spins through the vast void, and its sheer distance from the sun cloaks it in shadowy isolation. This is Uranus, a frozen enigma on the edge of our solar system. Unlike its planetary neighbors, Uranus refuses to play by the rules, defying expectations with its peculiar behavior and unexplained phenomena. What forces tilted it so drastically? Why does it emit so little heat compared to its peers? And could it be hiding oceans or even life beneath its icy surface? Today, we're embarking on a journey to uncover the 25 greatest mysteries of Uranus, each more perplexing than the last. From its chaotic moon system to its inexplicable magnetic field, this icy giant holds secrets that could reshape everything we know about the cosmos. So stay with us, because by the end of this video, you'll not only question what we know about Uranus, you might even rethink what we know about our universe. Now turning to one of the most striking mysteries of Uranus, we explore its jaw-dropping axial tilt of nearly 98 degrees. This unique feature sets it apart from every other planet in the solar system. To put that in perspective, most planets spin like tops, upright or slightly tilted, but Uranus rolls almost completely on its side as it orbits the Sun. Imagine a ball rolling around your feet rather than spinning upright. That's essentially what Uranus is doing. This odd behavior creates extreme seasons, with each pole getting 42 years of continuous sunlight followed by 42 years of darkness. But what could cause such a dramatic tilt in the first place? The leading theory suggests that during the early chaotic days of the solar system, a massive collision might have knocked Uranus over. Scientists believe this impact may have involved an Earth-sized object slamming into Uranus with enough force to permanently alter its orientation. This theory, while popular, only explains part of the story. If such a colossal event occurred, why doesn't Uranus show signs of significant internal heat, which ought to have been released from such a violent impact? And what about its moons and rings, which align with its tilted axis? Did they form after this collision, or were they somehow influenced by it? Other hypotheses involve gravitational tug-of-war games with neighboring planets, but these ideas remain speculative. To this day, no single explanation fully accounts for all the peculiarities of Uranus' tilt. It's a planetary puzzle that continues to elude scientists, reminding us how much we still have to learn about the formation and evolution of our solar system. As we dive deeper into the mysteries of Uranus, another perplexing question emerges: why is this planet so astonishingly cold? Among the outer planets of our solar system, Uranus stands out for its striking lack of internal heat. To illustrate, consider its neighbor, Neptune, which is roughly the same size and distance from the Sun. Despite these similarities, Neptune radiates much more heat into space, suggesting an active internal energy source. Uranus, on the other hand, barely emits any heat at all, leaving scientists scratching their heads. The planet's average temperature plunges to an icy -371 degrees Fahrenheit, making it one of the coldest places in our solar system. But what could have caused such a frigid disposition? Some researchers propose that Uranus may have suffered a catastrophic past, perhaps linked to the same collision that caused its dramatic axial tilt. This impact could have disrupted the planet's interior, ejecting or suppressing the heat that we would otherwise expect it to retain. Another idea considers Uranus' unique composition. Its core may be enveloped by an unusual layer of materials that trap heat, preventing it from radiating outward. While these theories offer intriguing possibilities, none fully solve the puzzle, as they fail to account for why Uranus differs so drastically from Neptune, a planet with a similar formation history. For now, this lack of internal heat remains a chilling enigma, one that scientists hope to unravel through further exploration and study. Moving ahead, let's examine the peculiarities of Uranus' atmosphere and the strange weather patterns that add more intrigue to this icy giant. Shifting our attention to the skies of Uranus, we encounter yet another enigma, its bizarre atmosphere and puzzling weather patterns. Uranus' atmosphere is dominated by hydrogen and helium, but it is the noticeable presence of methane that gives the planet its striking blue-green hue. Methane absorbs red light from the sun and reflects blue, but beyond its vibrant color lies an atmospheric system that defies expectations. Unlike other gas giants, Uranus exhibits surprisingly few visible storms or cloud formations, despite winds that can reach speeds of up to 560 miles per hour. These winds, among the fastest in the solar system, would normally suggest an active and turbulent weather system. Yet Uranus remains eerily calm, with only occasional and faint cloud bands observed. What makes this weather so unusual? One possible factor is Uranus' great distance from the Sun, which means it receives far less solar energy to drive atmospheric dynamics compared to planets closer to the Sun. However, this explanation falls short when considering Neptune, an equally distant planet with much more vigorous storm activity. Another theory points to the planet's internal dynamics. Uranus' lack of significant internal heat, as mentioned earlier, might mean that it has less energy to fuel dramatic atmospheric phenomena. Additionally, its extreme axial tilt could play a role, as the planet's poles experience decades of constant sunlight or darkness, creating unique seasonal effects that could influence its weather in ways we do not yet fully understand. Despite these theories, the precise mechanisms governing Uranus' subdued storms and unusual atmospheric behavior remain a profound mystery. This planet challenges our understanding of how weather works on distant worlds, leaving scientists eager to unlock the secrets hidden in its cloud tops. As we journey further, let's delve into the curious case of Uranus' magnetic field, which is just as peculiar as its weather. With the next phase of the journey in sight, let us explore the peculiarities of Uranus' magnetic field, a feature that sets it apart not only from Earth but also from other planets in the solar system. Unlike the magnetic field of Earth, which is closely aligned with its rotational axis and originates deep within its core, Uranus' magnetic field is a true oddity. It is tilted at an astonishing 59 degrees relative to its axis of rotation, and even more puzzling, it is significantly offset from the planet's center. This means that the magnetic field does not radiate evenly around Uranus, but instead displays a lopsided structure, with regions of stronger and weaker intensity scattered across the planet. Scientists have struggled to explain why Uranus' magnetic field exhibits such unconventional behavior. One compelling hypothesis suggests that the origin of this field may lie within a unique subsurface ocean composed of ionic or ammonia-rich water, where dissolved charged particles generate the magnetic forces. Another idea points to the possibility of a frozen mantle layer, where convection currents might be occurring in ways that are not yet fully understood. These theories indicate that the internal mechanisms of Uranus might differ vastly from those of other planets, but direct evidence remains elusive. This strange magnetic field also behaves erratically, with its interactions with the solar wind creating complex and unpredictable patterns. Auroras on Uranus, for example, do not align neatly with its poles as they do on Earth, resulting in faint and misaligned displays that add to the puzzle. The irregularity of the magnetic field poses major questions about the planet's internal structure and what might be driving such an unusual phenomenon. Understanding the magnetic field of Uranus could unlock vital clues about its composition and history, but for now, it remains one of the many riddles that this icy giant continues to guard. Moving forward, let us shift our attention to another intriguing aspect of Uranus, the origin and nature of its unusual spin and orbital path. As the next chapter of Uranus mysteries unfolds, we turn our gaze to its peculiar spin and orbital path traits that make this icy giant stand out in the solar system. Uranus rotates on its side, with its axis tilted at nearly a right angle to its orbital plane. This unusual orientation means that instead of spinning like a top, as Earth and most other planets do, Uranus appears to roll along its orbit like a barrel in space. Scientists suspect that such an extreme tilt is no coincidence, and many believe it could be the result of a cataclysmic event in the planet's distant past. Imagine an ancient collision with a massive celestial body, perhaps as large as Earth, striking Uranus during its early formation stages. The force of such an impact could have knocked the planet sideways, throwing its rotation off kilter. But the story is far from straightforward. If a collision did occur, it would have left lasting effects not just on Uranus' tilt, but also on its internal composition and thermal dynamics. Could this be connected to the planet's unusually low internal heat or its strange magnetic field? The answers remain hidden beneath layers of mystery. Some scientists propose an alternative theory involving gravitational interactions with other planets or even a massive passing object. In the chaotic early days of the solar system, close encounters between forming planets were not uncommon, and such interactions could have altered Uranus' spin and orbital path without the need for a direct collision. To add to this enigma, Uranus' orbit around the Sun is relatively circular, which raises further questions. If a significant impact occurred, why didn't it leave the planet with a more eccentric, elongated orbit? This inconsistency makes every explanation incomplete, leaving scientists to piece together clues from limited observations. Despite advanced computer simulations and models, none have yet provided a definitive answer. For now, Uranus' erratic spin and steady orbit remain a puzzle, suggesting a series of events so complex and improbable that we are only scratching the surface of understanding. As we ponder these cosmic mysteries, let us delve deeper into Uranus' surroundings by exploring the chaotic and unconventional nature of its moon system, another realm where surprises await. Now shifting our focus to the fascinating realm of Uranus moons, there's no shortage of mysteries to unravel. Uranus boasts an impressive collection of 27 known moons, each with its own unique quirks that set them apart from the satellites of other planets. What's particularly intriguing is the chaotic and unconventional nature of these moons' orbits and compositions. Unlike the neatly aligned moons of Jupiter or Saturn, many of Uranus' moons follow irregular, off-kilter paths, almost as if they're defying the usual rules of celestial mechanics. Take Miranda, for example, one of Uranus' most peculiar moons. Its surface is a bizarre patchwork of ridges, cliffs, and craters that seem almost stitched together in a haphazard manner. Some areas appear ancient and cratered, while others look relatively young and geologically active. This stark contrast has led scientists to suspect that Miranda may have experienced violent collisions or moments of intense internal activity that reshaped its terrain. One of its most famous features, the Verona Rupes Cliff, is believed to be one of the tallest known cliffs in the solar system, showcasing the dramatic and unexplained forces that have shaped this moon. Then there's the matter of the inner moons, which seem to exist in a tight, gravitationally complex dance with Uranus' faint rings. They interact in ways that remain poorly understood, creating a system that feels more like a cosmic puzzle than a predictable orbital arrangement. Scientists theorize that some of these moons may have formed from the remnants of past collisions, fragments coalescing over time into the irregular shapes we see today. Others speculate that the moons might have been captured from elsewhere in the solar system, their origins lying far from Uranus itself. But even the larger moons like Titania and Oberon have their share of mysteries. These icy worlds bear traces of geological activity that hint at possible subsurface oceans or tectonic movements, raising the tantalizing question of whether they could harbor conditions conducive to life. Yet, we're left with more questions than answers, as no spacecraft has visited Uranus moons in detail since the Voyager 2 made its brief flyby in the 1980s. What adds to the enigma is how Uranus' moon system as a whole seems so unlike that of its fellow outer planets. Whether it's the irregular orbits, unusual surface features, or the potential for hidden oceans beneath icy crusts, the chaos and diversity of Uranus moons continue to defy straightforward explanation. With such limited data and so many unresolved questions, the moon system offers a treasure trove of scientific puzzles waiting to be solved. As we explore these captivating satellites, it's impossible not to wonder what secrets they might reveal if we had the chance to study them up close. And speaking of hidden treasures, let's turn our attention to the planet's enigmatic rings, a feature that's as mysterious as it is mesmerizing. Shifting our gaze to the mysterious rings encircling Uranus, we encounter yet another puzzle that has left scientists scratching their heads. Unlike the bright, icy rings of Saturn that gleam brilliantly in reflected sunlight, Uranus rings are faint, dark, and far less reflective. Their dusky, almost shadowy appearance gives them an air of intrigue, and their composition has proven to be just as enigmatic. These rings are primarily made up of extremely small particles, likely composed of water ice mixed with a dark, unidentified material, possibly organic compounds or radiation-processed debris. The exact nature of this dark material, however, remains unclear, adding yet another layer of mystery to these celestial structures. What's particularly striking is how vastly different Uranus rings are compared to those of other gas giants. Take Saturn, for instance, whose rings are dazzling, expansive, and well-studied. In contrast, Uranus rings are narrow, sparse, and fragmented, almost as though they are reluctant to reveal their secrets. This has led scientists to ponder their origins. One leading theory suggests that the rings formed from the remnants of moons that were shattered by collisions or gravitational forces. Over time, the debris from these catastrophic events could have coalesced into the thin, dusty bands we observe today. Another hypothesis posits that Uranus may have captured stray material from the early solar system, with some of this debris eventually settling into ring formation. Yet, despite these ideas, no single explanation has been universally accepted. The composition, age, and even the dynamism of Uranus rings remain open questions. For instance, scientists are unsure whether these rings are ancient relics from Uranus formation or relatively young additions created by more recent cosmic events. Their faint appearance also raises questions about how they have managed to survive in such a seemingly fragile state for potentially billions of years. Without detailed observations, much of what we know is based on limited data collected during the Voyager 2 flyby in the 1980s, leaving many aspects of these rings shrouded in ambiguity. Adding to the intrigue is the way the rings interact with Uranus moons and magnetic field. The gravitational interplay between the moons and the rings appears to create an intricate system of influence that scientists are just beginning to study. Could these faint, dusty structures hold clues to the planet's tumultuous past, or do they hint at ongoing processes that we have yet to uncover? The truth is, the rings of Uranus stand as a quiet enigma, offering tantalizing glimpses into their secrets but keeping the full picture just out of reach. With so little direct exploration of Uranus to date, these rings continue to be one of the most fascinating and perplexing features of this distant world. As we delve deeper into the mysteries of Uranus, it becomes clear just how much there is left to discover. With the rings offering only part of the story, it's time to turn our attention to the strange and intricate behaviors of Uranus' magnetic field, a phenomenon that defies conventional expectations and continues to astonish researchers. With our attention now shifting to Miranda, one of Uranus' most captivating moons, we are met with a celestial body that defies explanation. Dubbed the Frankenstein moon by some, Miranda's surface is a patchwork of colossal cliffs, jagged ridges, and deep craters, unlike anything seen on other moons in the solar system. The most breathtaking of these features is Verona Rupes, a sheer cliff that towers approximately 12 miles high, making it the tallest known cliff in the solar system. To put that into perspective, it's more than 10 times the height of the Grand Canyon. Imagine standing at its edge, looking down into a seemingly endless abyss. It's a place that feels more like science fiction than reality. The chaotic and mismatched terrain of Miranda hints at a violent and mysterious past. Scientists have speculated that these bizarre surface features could be the result of massive impacts from external objects like asteroids or comets during the Moon's early history. Such catastrophic collisions may have shattered its crust, only for gravitational forces to pull the fragments back together in a haphazard manner, leaving behind the patchwork landscape we see today. Another widely debated theory involves tidal heating, a process where gravitational interactions with Uranus create immense friction within Miranda's interior, causing it to heat up and reshape its surface over time. However, the current lack of volcanic activity on Miranda raises questions about whether tidal heating could fully account for the Moon's unique features. Adding to the enigma, Miranda's surface appears to be a mix of both ancient, heavily cratered regions and relatively younger, smoother plains. This strange combination suggests that the Moon may have undergone multiple periods of geological activity, each rewriting parts of its surface while leaving other areas untouched. Yet, if these resurfacing events occurred, what triggered them? Was it a series of massive impacts, internal processes, or perhaps a completely unknown mechanism? Without more detailed data, the answers remain elusive. Miranda's irregular orbit around Uranus also complicates theories about its formation and history. Unlike many moons in the solar system that follow predictable paths, Miranda's orbital characteristics suggest a history of gravitational interactions, not just with Uranus but potentially with other moons. These interactions might have played a role in shaping its puzzling surface, but the specifics are still a topic of ongoing exploration. Despite its small size, Miranda continues to capture the imagination of scientists and space enthusiasts alike. Its surface, which looks like the remnants of a cosmic jigsaw puzzle, feels like a message from the distant past, yet we have no key to decipher it. As we ponder the mysteries carved into this moon's surface, it becomes clear just how much of the outer solar system remains a frontier of unknown. And while Miranda leaves us with more questions than answers, it also serves as a silent reminder of the dynamic and chaotic forces that have shaped Uranus and its moons over billions of years. With Miranda's mysteries still swirling in our minds, let us now explore an equally fascinating possibility lurking beneath the icy crusts of Uranus moons: the potential existence of alien oceans. As we venture further into the mysteries of Uranus' captivating moon system, an intriguing question emerges: could there be alien oceans hidden beneath the icy crusts of its moons? This possibility has sparked the imagination of scientists, especially when studying moons like Titania and Oberon, the two largest in Uranus' collection of 27. These cold, distant worlds may seem lifeless at first glance, but beneath their frozen surfaces, a whole new world might exist. The concept revolves around the presence of subsurface oceans, vast, liquid water reservoirs concealed under layers of ice. If confirmed, these hidden oceans could potentially reshape our understanding of where life might exist in the universe. So, how could these oceans form in such frigid conditions? Two key processes come into play here. The first is tidal forces. As these moons orbit Uranus, gravitational interactions create immense stress on their interiors, generating friction that produces heat. This heating could prevent the water below the icy shells from freezing entirely, maintaining it in a liquid state. The second process involves internal heating from the decay of radioactive materials within the moon's rocky cores. Combined, these forces might generate just enough warmth to sustain liquid water deep beneath the surface, creating a tantalizing possibility for habitability. Evidence supporting this hypothesis isn't entirely speculative. Scientists have studied similar phenomena on other moons in the solar system, such as Europa and Enceladus, which are known to harbor subsurface oceans. In fact, plumes of water vapor have been observed erupting from Enceladus, providing direct clues to the activity beneath its icy crust. Could Titania or Oberon share these traits? While no such plumes have been spotted so far, the conditions on these Uranian moons suggest it's not outside the realm of possibility. If these alien oceans do exist, the next question is whether they could support life. Life as we know it requires three key ingredients: liquid water, an energy source, and certain chemical compounds like carbon and nitrogen. Subsurface oceans heated by tidal forces or radioactive decay might provide two of these, water and energy. But what about the chemical building blocks? Some scientists speculate that comets or asteroids that collided with these moons in the past might have delivered the necessary organic materials, seeding the oceans with the ingredients for microbial life. While this idea remains unproven, it opens up an exciting avenue for future exploration. The search for oceans beneath Titania and Oberon is still in its infancy, but technological advancements could one day allow us to probe these distant moons more closely. Spacecraft equipped with radar capable of penetrating thick ice layers could reveal the hidden secrets below. If even a trace of liquid water is detected, it would be a monumental discovery, transforming these moons from cold, distant satellites into prime candidates in the search for extraterrestrial life. But until we gather more data, the true nature of these icy moons remains one of Uranus' most compelling mysteries. With this possibility captivating our imagination, we now turn our attention to the next layer of intrigue surrounding Uranus, its fascinating and distinct cloud formations. Moving forward into the captivating mysteries of Uranus, let us now unravel the enigma of its extraordinary cloud layers. Unlike the swirling, vibrant storms that dominate the atmospheres of Jupiter and Saturn, Uranus presents a more subdued but equally intriguing spectacle. The planet's clouds are primarily composed of methane ice, which plays a crucial role in giving Uranus its stunning blue-green hue. Methane absorbs red light from the sun, allowing only blue and green wavelengths to be reflected back into space. But the striking appearance of Uranus clouds is just the beginning. Their chemical makeup and behavior remain shrouded in mystery. One of the most peculiar aspects of Uranus clouds is their apparent lack of activity. While Jupiter is famous for its massive storms like the Great Red Spot, and Saturn is adorned with intricate bands of clouds and hexagonal polar patterns, Uranus seems comparatively featureless. Yet, this perception might simply be a result of how little we can see. The planet's cloud tops sit high above a thick atmosphere, with most dynamic weather patterns possibly concealed deep below. The limited data we have, mainly from the Voyager 2 flyby and Earth-based telescopes, hints at high wind speeds exceeding 500 miles per hour beneath the visible layers. However, why these winds don't manifest in large-scale storms or visible cloud formations on the surface remains a puzzle. The differences in Uranus clouds are not limited to their appearance. Their chemical composition also sets them apart. While hydrogen and helium dominate the atmospheres of Jupiter and Saturn, Uranus' atmosphere contains higher concentrations of methane and other compounds like hydrogen sulfide. This intriguing blend may contribute to the planet's unusually uniform coloration and could hold clues about its unique atmospheric processes. For instance, methane clouds occasionally condense into brilliant white patches, providing rare glimpses of dynamic activity. Yet, these fleeting changes raise more questions than answers. Are these isolated events caused by deeper atmospheric upheavals, or are they merely seasonal phenomena influenced by Uranus' peculiar axial tilt? Adding to the mystery is Uranus' extreme distance from the Sun, which leaves it with only a fraction of the solar energy that drives weather on other planets. Despite this, its atmosphere exhibits some of the fastest winds in the solar system. This paradox begs the question, what energizes these winds? Is the planet's internal heat contributing to these dynamics, or are there entirely unknown mechanisms at play? Unlike Neptune, which has a similar composition but radiates internal heat, Uranus emits almost no measurable heat. This absence of a strong internal heat source makes the behavior of its clouds and winds even more perplexing. The scarce information we have about Uranus cloud patterns highlights the need for further exploration. Advanced telescopes and future space missions could provide invaluable data, potentially uncovering hidden layers of complexity in the planet's atmosphere. Understanding Uranus clouds not only deepens our knowledge of this distant world, but also sheds light on atmospheric phenomena that may occur on other ice giant planets across the universe. As we continue to puzzle over the mysteries of Uranus clouds, let us now turn to another wonder of this icy giant, its faint yet fascinating aurorae. As we shift our attention to yet another fascinating mystery, Uranus' faint and unusual aurorae illuminate a puzzling chapter in the story of this icy giant. Unlike the vibrant and well-studied aurorae on Earth, which dazzle with their brilliant displays of color, the aurorae on Uranus are far weaker, dimmer, and oddly elusive. These faint lights are caused, like on other planets, by charged particles from the solar wind interacting with the planet's magnetic field. However, the mechanics of how this process unfolds on Uranus remain a profound enigma. One of the key challenges in understanding Uranus' aurorae lies in the planet's oddly skewed magnetic field. Unlike Earth's magnetic field, which is neatly aligned with its rotational axis, Uranus' magnetic field is tilted at a staggering 59 degrees relative to its spin. Even more peculiarly, it does not originate from the planet's core but is offset, as if the magnetic field is carelessly shifted to one side. This misalignment means that as Uranus rotates, its magnetic field wobbles unpredictably, making it exceedingly difficult for scientists to model and predict the behavior of its aurorae. Contributing to the complexity is Uranus' extreme axial tilt. With the planet spinning almost on its side, its poles take turns facing the sun directly, creating unique seasonal effects that could impact the aurorae. On Earth, aurorae are concentrated around the polar regions due to the shape and alignment of our magnetic field. But on Uranus, this sideways orientation combined with its erratic magnetic field could scatter auroral activity unpredictably across the planet, making it even harder to track and study. Adding to the intrigue, the aurorae on Uranus are thought to be faint because the planet's distance from the sun drastically reduces the intensity of the solar wind it encounters. Unlike the robust streams of charged particles that fuel the dazzling aurorae on Earth or Jupiter, the solar wind at Uranus is much weaker, potentially contributing to the subdued nature of its auroral displays. And yet, the fact that these faint phenomena occur at all raises the question of what other processes beyond solar wind interactions might be at play. The few glimpses we have had of Uranus' aurorae, largely thanks to the fleeting Voyager 2 flyby and advanced Earth-based observations, offer tantalizing clues but no definitive answers. Could there be unknown interactions between Uranus' peculiar magnetic field and its internal structure driving these faint lights? Or might the unique chemical makeup of the planet's atmosphere play an unexpected role? Without closer and more detailed observations, these questions remain open, leaving scientists to theorize and speculate. The mysterious aurorae of Uranus invite us to confront how little we truly understand about the dynamics of magnetic fields and atmospheric interactions on ice giants. Unlocking the secrets behind these dim lights could not only reveal more about Uranus, but also deepen our understanding of similar phenomena on exoplanets across the galaxy. As we ponder the mysteries glowing faintly within Uranus' magnetic field, let us take another leap forward and unravel the peculiarities of its extreme day-night cycle, a phenomenon just as strange and intriguing. As the next chapter of Uranus mysteries unfolds, we encounter one of the most peculiar aspects of this ice giant, its extraordinary day-night cycle. Unlike anything experienced on Earth, Uranus' extreme tilt of nearly 98 degrees means that its poles spend decades bathed in continuous sunlight, only to then endure equally long periods of total darkness. Imagine standing at Uranus' North Pole and witnessing 42 Earth years of unbroken daylight, followed by 42 years of night, a phenomenon so alien that it challenges our understanding of planetary behavior. This prolonged exposure to sunlight, or lack thereof, has profound implications for the planet's atmosphere and weather. Scientists believe that such extensive cycles could affect how heat is distributed across the planet, potentially driving the unusual atmospheric patterns observed on Uranus. During the decades-long days, one might expect increased atmospheric activity as sunlight warms the methane-laden clouds. Conversely, the decades of darkness could lead to extreme cooling and unique weather phenomena that remain largely unexplored due to the lack of observational data. Interestingly, this extreme tilt is also responsible for creating seasons on Uranus that are unlike any other in the solar system. Each season lasts approximately 21 Earth years, dramatically altering what little we know about the planet's climate dynamics. Could these prolonged cycles of light and dark explain the surprising lack of visible storms on Uranus compared to its planetary neighbors? Or might the planet's internal structure play a mitigating role, preventing the kinds of atmospheric disturbances seen on Jupiter or Saturn? Adding to the intrigue is the question of how this unusual cycle impacts the movement of winds and gases around the planet. On Earth, seasonal changes lead to predictable shifts in weather patterns, but Uranus seems to defy such expectations. Without a clear understanding of how sunlight, or the absence of it, interacts with the planet's atmosphere, scientists are left piecing together theories from limited data, primarily gathered during Voyager 2 flyby and Earth-based telescopic observations. Unlocking the secrets of Uranus' day-night cycle could shed light on the broader mechanics of planetary atmospheres, not just in our own solar system, but also on distant exoplanets that might share similar traits. As we marvel at this remarkable cycle of endless days and nights, our curiosity naturally shifts to another enigma of Uranus, its isolated position in the solar system and how it may have arrived at this distant locale. As we shift our gaze to yet another fascinating piece of Uranus' puzzle, its remote location within the solar system takes center stage. Positioned more than 1,780,000,000 miles from the Sun, Uranus resides in the cold outer reaches of our planetary neighborhood, far removed from the bustling activity of the inner planets. This raises a compelling question. How did this icy giant come to occupy such an isolated position? Scientists believe the answer might be hidden in the chaotic early days of the solar system's formation. During this tumultuous period, young planets were not yet settled into their current orbits and were influenced by powerful gravitational forces exerted by one another. One theory suggests that Uranus, along with its sibling Neptune, may have initially formed closer to the Sun. However, as the massive gas giants Jupiter and Saturn shifted positions, their immense gravitational pull could have acted like a cosmic slingshot, flinging Uranus outward to its current distant orbit. This notion of planetary migration provides a tantalizing glimpse into the forces that may have shaped the solar system as we know it. Adding to the complexity is the possibility that Uranus' isolation was influenced by massive collisions with other large objects in ancient times. Such cataclysmic events could have altered not only its orbit but also its unique sideways tilt, further separating it from its planetary peers. These collisions, or perhaps a series of them, might have disrupted Uranus' early trajectory, pushing it into a solitary path. Another perspective to consider is the role of the Sun's early protoplanetary disk, the swirling cloud of gas and dust from which all the planets formed. Variations in the density and composition of this disk might have led Uranus to accumulate more icy material, anchoring it farther from the Sun. Could this explain why Uranus is classified as an ice giant rather than a gas giant like Jupiter or Saturn? The interplay between these early conditions and Uranus' current state continues to challenge our understanding. Even today, this distant position affects how we study the planet. With only a single flyby from Voyager 2 and limited telescopic observations, Uranus' mysteries remain particularly elusive compared to those of planets closer to Earth. Yet, this isolation is also what makes Uranus so intriguing. By unlocking the secrets of its current location and the journey it has taken through the solar system, scientists hope to not only better understand Uranus itself, but also gain insights into the broader mechanics of planetary migration and formation. As we ponder these cosmic forces that have left Uranus so distantly placed, we turn our attention to yet another captivating question. What do we truly know about the formation of Uranus' mysterious core? With the next phase of the journey in sight, we now delve into the heart of Uranus quite literally, as we explore the mystery surrounding the formation of its elusive core. Unlike Earth, whose core has been extensively studied, Uranus' core remains shrouded in uncertainty, primarily due to the lack of direct measurements. What we do know, largely inferred from its mass and gravitational field, suggests that this core could consist of heavier elements like rock and ice, distinguishing it from the primarily hydrogen-helium makeup of gas giants like Jupiter and Saturn. But what exactly lies within this icy giant remains an open question. One prevailing theory is that Uranus formed in a region of the early solar system rich in icy and rocky materials, which then coalesced under immense pressure to create a dense, layered core. This core, possibly surrounded by a fluid mantle of water, ammonia, and methane, may have played a critical role in shaping the planet's overall structure and atmospheric characteristics. However, without direct samples or advanced spacecraft measurements, even these educated guesses remain speculative. Adding to the enigma is the question of how this core was affected by the same catastrophic events that might have tilted Uranus on its side. Could a massive collision or series of impacts have disrupted its internal layers, mixing heavier and lighter materials in ways we have yet to comprehend? Such events may have permanently altered not only its physical makeup but also its thermal dynamics, potentially explaining why Uranus emits so little heat compared to its sibling planet, Neptune. The composition of Uranus' core also raises broader questions about planetary formation. Did it accumulate its heavy elements through gradual accretion in a quiet, stable environment, or was its formation a chaotic process influenced by dynamic interactions with other young planets? With its isolated position in the solar system and its unique classification as an ice giant, Uranus offers a rare opportunity to study planetary diversity and evolution. Yet, the lack of close-up missions to Uranus has left its core as one of the great unknowns of our cosmic neighborhood. Advances in space exploration technology could one day allow us to probe beneath its outer layers, unveiling secrets locked away for billions of years. Until then, the formation of Uranus' core remains as mysterious as the planet itself, a reminder of just how much there is still to learn about the unseen depths of our solar system. As we leave this intriguing mystery behind, our next step takes us to an equally captivating topic: the odd relationship between Uranus' moons and rings. As we pivot to another fascinating puzzle, let's unravel the peculiar and complex relationship between Uranus' moons and its rings. Unlike the iconic bright, icy rings of Saturn, Uranus' rings are faint and dark, composed of mysterious materials we do not fully understand. Surrounding these enigmatic rings are 27 known moons, each with distinct characteristics and irregular orbits that seem to defy easy categorization. This unique configuration raises a compelling question. Are the moons and rings connected in ways we are only beginning to theorize? One intriguing possibility is that the rings could be remnants of former moons that were shattered by massive collisions. Over billions of years, the debris from these catastrophic events might have spread out and formed the narrow, dusty rings we see today, but the reverse could also be true. Material from the rings driven by gravitational interactions or other forces might be falling onto the moons, gradually altering their surfaces and even their chemical compositions over time. This two-way exchange, if confirmed, would provide a dynamic snapshot of how celestial bodies interact and evolve within a system. Adding to this complexity is the fact that some of Uranus' inner moons, like Bianca and Cressida, orbit so close to the rings they may be influencing their structure. The gravitational pull of these moons could create subtle gaps or distortions in the rings, further complicating the story. Alternatively, the motion of the rings may be affecting the stability of the moon's orbits, potentially nudging them into new paths over geological timescales. Another layer of intrigue comes from the variety within Uranus moons themselves. While some, like Miranda, display bizarre geological features hinting at violent histories, others are more uniform and subdued. Could the ongoing interplay between the moons and rings explain these differences? And if so, how does this system compare to other planets with rings and moons like Saturn or Jupiter? Each of these questions underscores just how little we know about the mechanics of Uranus' unique celestial ballet. The lack of direct exploration only deepens the mystery. Future missions equipped to study the gravitational dynamics and chemical exchanges within this system could provide groundbreaking insights. Imagine spacecraft capable of closely observing how the moons and rings interact, tracing the flow of materials, and identifying whether the rings are gaining mass, losing mass, or remaining in a delicate balance. These observations could transform our understanding of not just Uranus, but also the fundamental processes that shape planetary systems throughout the universe. For now, the odd and intricate relationship between Uranus moons and rings remains an active frontier of discovery, a tantalizing reminder of how much this distant planet still has to teach us. As we move forward, let's shift our gaze to yet another captivating feature of Uranus, the reasons behind its striking blue-green color and why it differs from its fellow ice giant Neptune. Shifting our focus to a visual marvel, let's unravel the mystery behind Uranus' mesmerizing blue-green hue. At first glance, the planet's soft, tranquil color seems simple to explain. Methane in its atmosphere absorbs red light from the sun and reflects blue light back into space, creating that iconic shade. But here's where the enigma begins. If this same mechanism is at play on Neptune, why does Neptune display a more vivid, deeper blue in comparison to Uranus' paler tones? Despite similar atmospheric compositions, this stark difference remains a puzzle. One theory suggests that Uranus might have an additional haze layer in its upper atmosphere, acting almost like a filter that mutes its colors. This haze could be a result of different chemical reactions unique to Uranus, possibly influenced by its colder temperatures or weaker internal heat. Unlike Neptune, which radiates more heat from its core, Uranus appears to lack significant internal warmth. This absence of heat might contribute to slower atmospheric dynamics, leading to a buildup of haze particles that dull its vibrancy. Another possibility is linked to the subtle differences in methane concentration or trace chemicals between the two planets. Even slight variations in these elements could alter the way light interacts with their atmospheres, resulting in Uranus' softer color. Scientists have proposed that other compounds, like hydrogen sulfide, might also play a hidden role, although direct evidence is still lacking. Some even speculate that Uranus' unique axial tilt, rotating almost sideways compared to other planets, might influence how its atmosphere develops over long periods. This extreme tilt exposes different regions of the planet to prolonged sunlight or darkness, potentially affecting chemical processes that dictate its overall appearance. These unanswered questions highlight not only the complexity of Uranus' atmosphere, but also how much we still need to learn about the interplay of light, temperature, and chemistry on distant worlds. With advanced technology and upcoming missions, scientists hope to peel back the layers of Uranus' atmosphere, seeking the precise reasons behind its muted elegance. But for now, the planet's subdued, mysterious glow stands as a testament to the challenges and wonders of exploring the unknown. Moving ahead, let us dive into another intriguing anomaly. Why is Uranus' gravitational field surprisingly weak compared to other gas giants? With the next layer of mysteries waiting to unfold, let us explore why Uranus possesses a gravitational field that is surprisingly weak compared to its fellow gas giants. At first glance, Uranus, being the third largest planet in our solar system, would be expected to exert a powerful gravitational pull. After all, its size suggests a significant mass beneath its icy layers. Yet when measured, Uranus' gravitational force is much weaker than that of Jupiter or Saturn, leaving scientists puzzled about what lies beneath its cloudy surface. A leading hypothesis points to Uranus' unique composition and internal structure. Unlike Jupiter or Saturn, which are primarily made of hydrogen and helium, Uranus is classified as an ice giant, with a significant portion of its mass thought to consist of heavier elements like water, ammonia, and methane in a frozen state. These materials are denser, yet the overall distribution of mass within Uranus might be more spread out, reducing its gravitational impact at the surface. In simpler terms, its mass may not be as tightly packed or concentrated as we see in other gas giants, weakening the gravitational pull. Another factor could be linked to its relatively small core. While the cores of Jupiter and Saturn are believed to be dense and massive, Uranus may have a smaller, less defined core, surrounded by a thick mantle of ices and gases. This would mean less mass at its center to generate the kind of gravitational force observed on its larger cousins. However, without direct measurements or a closer investigation of Uranus' interior, these insights remain speculative. The planet's unusual tilt might also play an indirect role. Rotating nearly sideways, Uranus experiences extreme seasonal shifts, which could influence the distribution of its atmospheric and internal materials. This redistribution might subtly impact the measurement of its gravitational field, although the exact mechanics of this relationship remain unclear. The weaker gravity of Uranus has profound implications for its atmosphere and moons. The planet's atmosphere is relatively shallow and less dense, which might contribute to its limited storm activity compared to the more chaotic weather systems observed on Jupiter or Saturn. For its moons, a weaker gravitational field means that their orbits are less tightly bound, possibly explaining why some of Uranus' moons have irregular, chaotic trajectories. This dynamic adds another layer of complexity to understanding the planet's relationship with its satellite system, yet significant gaps in our understanding persist. What if Uranus' weak gravity is hiding something unexpected about its core or mantle? Could there be unknown materials or processes at play that we have yet to uncover? Scientists remain eager to answer these questions, but without dedicated missions to study the planet in detail, we can only scratch the surface of this enigma. As our journey continues, let us now turn to an equally perplexing aspect: the origins and abundance of methane in Uranus' atmosphere, a key ingredient that paints the planet's remarkable face. Now shifting our focus to a fascinating and colorful mystery, let us examine the origins of methane in Uranus' atmosphere, the very substance responsible for its striking blue-green appearance. At the heart of this enigma lies a simple yet profound question: how did so much methane become an integral part of Uranus' atmospheric makeup? Methane, a compound of carbon and hydrogen, plays a pivotal role in shaping how the planet reflects sunlight, absorbing red wavelengths and leaving behind the vivid hue that makes Uranus so visually distinct. But its presence in such high quantities raises intriguing questions about the planet's history and formation. One theory suggests that the methane now found in Uranus' atmosphere was originally trapped during the planet's formation, at a time when the solar system was a chaotic and violent place. As Uranus formed from a swirling disk of gas and dust, methane could have been captured within the planet's icy layers, accumulating over time. The extreme cold in the outer reaches of the solar system would have allowed methane and other volatile compounds to condense and integrate into the developing planet. This idea aligns well with Uranus' classification as an ice giant, where heavy elements like methane, ammonia, and water make up a significant portion of its composition. Another possibility points to external factors, such as the delivery of methane by comets or other icy bodies that collided with Uranus during its early years. These objects, rich in frozen gases, could have deposited significant amounts of methane into the planet's developing atmosphere as they impacted its surface or were captured by its gravitational field. Such events not only introduce methane, but might also explain other traces of chemical diversity in Uranus' atmosphere. Interestingly, the abundance of methane on Uranus is also what sets it apart from its so-called twin, Neptune. Both planets are structurally similar, yet the shade of Neptune's color appears deeper and more vibrant. This raises further questions about whether Uranus' methane concentration is linked to unique conditions during its formation, its internal dynamics, or perhaps even unknown processes in its atmosphere that differentiate it from Neptune. Could there be subtle chemical interactions or even missing compounds that alter how methane behaves on Uranus? The mystery of methane goes beyond its impact on Uranus' color. Understanding its origins can offer valuable insights into the broader story of how planets like Uranus formed and evolved, as well as how icy bodies in the outer solar system interact with their environments. Methane's story on Uranus might even hold clues to the histories of other distant worlds, both within our solar system and beyond. As we continue piecing together the puzzle, let us now uncover whether Uranus' geological past harbors even more surprises. Could the planet have once been more active and dynamic than we currently imagine? Let us dive deeper. As we shift our focus to yet another captivating question, let us explore whether Uranus could have experienced a more active and dynamic past than what we observe today. While the icy giant currently appears calm and subdued, scientists wonder if it might have once harbored a warmer core, a stronger magnetic field, or even dramatic atmospheric dynamics that have since faded into obscurity. Understanding Uranus' geological history is like piecing together a puzzle with many missing pieces, but the clues we do have suggest a far more complex and intriguing story than meets the eye. Consider its core, for example. Unlike other gas and ice giants, Uranus radiates almost no excess heat into space, a characteristic that has left researchers scratching their heads. Could it be that the planet's core was once much warmer, generating enough internal heat to power a more vigorous internal or atmospheric system? Some theories suggest that a catastrophic event early in Uranus' history, like a massive impact, could have disrupted its heat flow, effectively shutting down the planet's thermal engine. If so, this would not only explain its mysteriously cold present state, but might also hint at a past when Uranus was more active, dynamic, and possibly even unpredictable. Then there is its magnetic field, which already defies convention by being tilted at a bizarre angle and offset from the planet's center. Such an irregular field raises questions about the processes at work deep beneath Uranus' icy layers. Was its magnetic field once stronger and more aligned, only to become distorted over time due to internal changes or external interactions? Perhaps shifts in the composition or movement within its interior altered the magnetic field's behavior, leaving us with the peculiar configuration we see today. The lack of detailed measurements makes these theories difficult to confirm, but they highlight how much remains unknown about the planet's early internal dynamics. And what about its atmosphere? Uranus' weather is relatively subdued compared to its neighbor Neptune, but could its skies have once been alive with dramatic storms, turbulence, or other atmospheric activity? Some scientists speculate that when the planet was younger, it may have had more pronounced atmospheric motions, powered by a combination of internal heat and the external influence of the distant sun. Over billions of years, such activity might have gradually diminished, leaving Uranus with the relatively placid appearance we observe now. The gaps in our knowledge about Uranus' evolutionary timeline are both frustrating and exciting. Without more detailed data from space missions, we are left with tantalizing hints of a more vibrant past but no concrete answers. However, every mystery brings us closer to asking the right questions. What events in Uranus' early history may have shaped the planet we see today? And how does its evolutionary journey compare to those of other planets in our solar system? With these thoughts in mind, let us now shift our gaze toward the potential links between Uranus and its so-called twin, Neptune. Could their shared characteristics hold the key to understanding why Uranus evolved into such a curious and enigmatic world? Now turning to the fascinating relationship between Uranus and Neptune, often referred to as the ice giant twins, we begin to unravel a tale of similarities that mask striking differences. At first glance, these distant planets appear to share a lot in common. Both are classified as ice giants composed largely of hydrogen, helium, and water, ammonia, and methane ices. Their vivid blue hues, shaped by methane in their atmospheres, make them stand out in the solar system as sibling worlds. However, as we look closer, deviations in their physical characteristics and behaviors tell us a more complex story, one that raises compelling questions about their shared origins. For one, while both planets are similar in size, Uranus is slightly larger in diameter, yet it holds less mass than Neptune. This difference in density hints at variations in their internal compositions, which could stem from how and where they formed during the chaotic early days of the solar system. Could it be that Uranus and Neptune started their lives in different regions of the protoplanetary disk, only to migrate to their current locations over time? Or perhaps powerful interactions with other early planets shaped them in distinct ways. These uncertainties make their developmental paths a fascinating puzzle for scientists to piece together. Then there is the curious matter of their atmospheric and magnetic behaviors. While Uranus surprises us with its subdued weather patterns and almost non-existent internal heat radiation, Neptune exhibits far more dynamic storm activity and radiates more heat into space despite their similar distances from the Sun. Why would two planets that seem so alike on the surface have such drastically different energy profiles? These atmospheric divergences could point to differences in their internal heat engines or possibly the aftermath of unique events in their histories, like massive impacts or unusual gravitational interactions. The differences extend even further when we examine their magnetic fields. Neptune's magnetic field, though also tilted and offset, does not display the same level of irregularity seen in Uranus. This raises the question of whether the two planets' magnetic fields developed under different circumstances, or if Uranus underwent a dramatic event that permanently disrupted its magnetic structure. Understanding these distinctions may hold the key to unlocking the secrets of their subsurface dynamics. And let's not forget their moons and rings. Neptune's moon Triton, with its retrograde orbit, stands out as a likely captured object, possibly a former dwarf planet from the Kuiper belt. Uranus moons, on the other hand, display irregularities and chaotic orbits that hint at a violent past within its system. Could these differences reflect the unique gravitational environments in which each planet operates? Or do they tell us more about the forces Uranus and Neptune faced during their formation? As we connect these dots, the duality of Uranus and Neptune becomes a mirror to the broader mysteries of planetary formation and evolution. Are they truly twins, shaped by the same cosmic forces but altered by individual fates? Or are they more like distant cousins, their similarities merely superficial, masking deeper and more distinct origins? To probe these questions, we need both imagination and further exploration. Moving ahead, let's consider why Uranus has been largely overlooked by space missions, a puzzling gap in our quest to understand the solar system's most enigmatic planets. Shifting our focus now to a question that leaves many space enthusiasts scratching their heads, we arrive at the puzzling neglect of Uranus by space exploration missions. Despite its fascinating features and countless unresolved mysteries, Uranus has largely been sidelined when it comes to dedicated space missions. In fact, our most detailed look at this icy giant came way back in the year 1986, when Voyager 2 performed a quick flyby, spending only a brief time capturing images and collecting data before hurtling onward. While the spacecraft's visit offered groundbreaking insights, what it provided was only a snapshot, a fleeting glimpse that barely scratched the surface of this enigmatic planet. This lack of attention raises an important question. Why has Uranus been so overlooked, especially when compared to planets like Mars, Jupiter, or even Saturn? One potential reason lies in its immense distance from Earth. Positioned at an average of nearly 1.8 billion miles away from our planet, Uranus presents enormous logistical challenges for mission planning. Sending a spacecraft to Uranus not only requires significant time, with travel taking over a decade, but it also demands advanced technology capable of operating in its cold, distant environment. These factors make missions to Uranus logistically complex and, not surprisingly, incredibly expensive. Another factor could be the competition for resources. With limited funding and priorities often focused on planets like Mars, which holds more immediate potential for understanding habitability and past life, Uranus tends to fall lower on the list of exploration priorities. Missions to the gas giants Jupiter and Saturn have also taken precedence, given their larger size, more dramatic weather systems, and striking features like Saturn's famous rings or Jupiter's great red spot. In comparison, Uranus, with its quieter storms and less visually dramatic appearance, may seem less urgent to explore, at least to those allocating budgets. However, this lack of exploration comes with steep scientific costs. Without dedicated missions, our understanding of Uranus remains woefully limited. Fundamental questions about its internal structure, atmospheric chemistry, and mysterious moons remain unanswered. For example, the unusual tilt of its rotational axis, the bizarre behavior of its magnetic field, and the potential for subsurface oceans on its moons are topics that demand closer inspection. Further, the lack of up-close data hinders our ability to compare Uranus to other planets, including its so-called twin Neptune, leaving critical gaps in our broader understanding of planetary science and the formation of icy giants. The flyby of Voyager 2 revealed tantalizing clues such as faint, dark rings and unexpected variations in temperature across Uranus' atmosphere. Imagine the depth of knowledge we could gain with modern technology capable of making detailed observations for years rather than just moments. Scientists have proposed ambitious missions, from orbiters that could study the planet in detail to probes designed to dive into its atmosphere, but so far these plans remain on the drawing board. Ultimately, ignoring Uranus means turning away from one of the solar system's last great frontiers. As we look to the future, some exciting possibilities are emerging, with international space agencies expressing growing interest in exploring Uranus in the coming decades. If and when a dedicated mission materializes, it promises to be a monumental step forward in uncovering the secrets of this icy enigma. But until then, Uranus remains a distant, haunting mystery, silently urging us to turn our eyes back toward it. Speaking of mysteries, let us now venture even further into speculation as we ponder whether Uranus could, in any way, offer even the faintest glimmer of hope for supporting life. Now turning to the intriguing notion of life, let us consider whether Uranus could hold even the faintest potential for supporting it. While the idea might sound far-fetched at first, scientists have speculated about the possibility of life existing in the hidden, subsurface oceans potentially lurking beneath the icy crusts of Uranus' larger moons like Titania and Oberon. These moons are thought to harbor vast layers of water beneath their frozen surfaces, kept in a liquid state by internal heating generated through tidal forces. Water, as we know, is one of the key ingredients for life, and its presence raises the tantalizing question: could these oceans be home to microbial life forms, similar to extremophiles found in some of Earth's most inhospitable environments? However, the challenges of life on or near Uranus are enormous. The extreme cold, with temperatures plunging to around -371 degrees Fahrenheit, creates an environment that seems, at first glance, utterly inhospitable. The thick layers of ice and rock that likely enclose these subsurface oceans would also make it incredibly difficult for energy sources, such as sunlight, to penetrate. Without light, life would have to rely on alternative energy sources, such as chemical reactions, a phenomenon observed in hydrothermal vent ecosystems deep beneath Earth's oceans. Yet, even if these conditions exist on Uranus moons, there's no conclusive evidence to confirm that life could thrive in such a remote and alien world. Another hurdle is the lack of essential data to support or refute these possibilities. Since no spacecraft has conducted close-up studies of Uranus moons in detail, our current understanding of their composition and potential habitability is based entirely on indirect observations and theoretical models. This leaves us with more questions than answers, including whether these moons possess the necessary chemical building blocks for life, such as organic molecules, or whether their oceans are stable enough over long periods to sustain even the simplest life forms. Still, the speculative allure of Uranus as a harbor for life isn't entirely unfounded and serves as a reminder of the vast unknowns that await us in our own solar system. Even if the moons of Uranus turn out to be sterile, learning about their environments could significantly advance our understanding of where life might exist elsewhere in the universe. After all, studying the extremes of habitability forces us to broaden our definitions of what life requires and how it might adapt to conditions we once deemed impossible. As we ponder this mystery of potential life, one thing becomes clear: exploring Uranus moons could yield revolutionary insights, not just about their environments, but about life's resilience in the cosmos. And with that thought in mind, let us now shift our focus to another perplexing puzzle: the role Uranus might have played in shaping the early history of our solar system. As we delve further into the mysteries of Uranus, let us consider the enigmatic role this icy giant may have played in the formation of our solar system. Unlike the inner planets, whose histories are more extensively studied, Uranus occupies a distant and largely overlooked corner of our cosmic neighborhood. Yet, its very presence and peculiar traits offer tantalizing clues about the chaotic processes that shaped the solar system billions of years ago. One prevailing theory suggests that Uranus, along with other giant planets, may have been instrumental in sculpting the orbits of smaller celestial bodies, such as asteroids and comets, during the early days of planetary formation. Its immense gravitational pull could have acted like a cosmic shepherd, influencing the trajectories of surrounding debris and possibly even ejecting some objects out of the solar system entirely. However, Uranus' unique characteristics, like its extreme axial tilt and peculiar magnetic field, raise questions about whether it experienced dramatic events that altered its original role in this formative period. Was it involved in violent gravitational interactions with other planets, such as Neptune, that reshaped their orbits and positions? Or did it suffer a catastrophic collision early in its history, changing not only its orientation but also its capacity to contribute to the larger dynamics of the solar system? These questions remain unanswered, largely due to the lack of direct exploration and data about this distant planet. Adding to the intrigue, Uranus' current position in the solar system also sparks curiosity. Its placement far beyond the asteroid belt and closer to the outer edges of the planetary system might suggest that it migrated from a different location during the solar system's infancy. Planetary migration is a well-documented phenomenon in which giant planets shift from their original positions due to gravitational interactions with the surrounding protoplanetary disk or other planets. If Uranus did migrate, it could have left a trail of disruption in its wake, altering the distribution of material in the solar system and influencing the formation of other planets, moons, and even satellites. Despite these compelling theories, an overarching mystery lingers. How much of Uranus' past is hidden beneath its icy layers, waiting to be revealed? Without extensive exploration missions to examine its structure, atmosphere, and environment in greater detail, we are left with piecemeal conjectures about its role in a much larger cosmic story. Understanding Uranus' part in the orchestration of the early solar system could unlock not only its enigmatic past but also provide broader insights into how planetary systems develop around other stars. And as we consider these possibilities, let us take a closer look at yet another confounding mystery: the composition of Uranus' atmosphere and the secrets it may conceal. As the next enigma unfolds, let us delve into the mysterious composition of Uranus' atmosphere, a realm that continues to baffle scientists with its unusual chemistry and dynamics. Unlike the more familiar atmospheres of Earth or even Jupiter, Uranus' envelope of gases hides secrets that are only partially understood. Its pale blue-green hue, created by the absorption of red light due to methane gas, is just the beginning of its atmospheric story. Beneath this simple facade lies an intricate blend of elements including hydrogen, helium, and methane, with trace amounts of substances like hydrogen sulfide. This particular compound, hydrogen sulfide, is of great interest because it gives the clouds their characteristic makeup and may hold clues about the planet's formation and evolution. On Earth, hydrogen sulfide is notorious for its unmistakable rotten egg smell, but on Uranus, it plays a far more complex role. One of the most puzzling aspects of Uranus' atmosphere is the uneven distribution of these elements, as well as their interactions under extreme conditions. Scientists have speculated that variations in temperature and pressure within the planet's upper atmosphere might influence the chemical reactions, yet the exact processes remain unknown. For instance, why do some regions of the atmosphere seem to lack significant cloud activity, while others occasionally form bizarre methane ice clouds? And how do these trace compounds, such as hydrogen sulfide and ammonia, contribute to weather phenomena unlike anything observed on other planets? The lack of detailed exploration leaves these questions hanging, with only distant telescope observations and data from a single flyby mission offering clues. Adding to the complexity is Uranus' frigid climate, with temperatures colder than any other planet in the solar system. This extreme cold poses unique challenges for atmospheric chemistry, potentially slowing or altering reactions in ways we can only hypothesize about. Such conditions might prevent the kind of dynamic weather systems seen on Jupiter or Saturn, which are known for their swirling storms and dazzling vortices. Yet, Uranus does experience winds that can reach speeds of hundreds of miles per hour, hinting at an underlying energy source that scientists struggle to explain. Could these winds carry specific chemicals across different layers of the atmosphere, redistributing elements like methane and hydrogen sulfide in unexpected ways? Or are the deeper mysteries tied to the planet's internal structure, influencing not just the surface but the behavior of its gases? Even with these tantalizing possibilities, our current understanding of Uranus' atmosphere is incomplete at best. Without closer observation and sampling, we can only build models and speculate about how its chemical stew behaves over time. Yet, any deeper insight could have far-reaching implications, not just for solving Uranus' mysteries, but for understanding atmospheric processes on other icy giants scattered throughout the universe. As we grapple with these challenges, another essential question emerges: what lies beneath the planet's icy layers, and could these hidden depths hold more answers to the secrets we've uncovered so far? As the final curtain rises on our journey through Uranus enigmas, we arrive at perhaps the most profound mystery of all. What secrets lie beneath its icy exterior? Beneath the planet's pale, serene surface exists a world that remains almost entirely hidden from our understanding. Scientists suspect that Uranus' outermost layers, composed largely of hydrogen, helium, and methane, give way to an expansive interior of exotic materials under immense pressure and temperature. But what exactly lies within this unseen realm has sparked countless theories. One possibility is the existence of a vast ocean-like layer of water, ammonia, and other volatile compounds, often referred to as a supercritical fluid. In this extreme environment, these substances could behave in ways that defy our earthly experiences, blending the properties of liquids and gases. Such a layer might also serve as a medium for mysterious magnetic processes, potentially explaining Uranus' bizarre and off-center magnetic field. It raises the mind-bending question: could this hidden ocean-like layer hold the key to understanding not just Uranus, but magnetic mysteries across the cosmos? Further down, the theoretical core of Uranus adds to the intrigue. Thought to be composed of rock and various metals, this core could differ drastically from those of other planets, shaped by the planet's unique history of violent collisions or early solar system interactions. If Uranus' core is smaller or less dense than expected, it could help explain why the planet emits so little internal heat compared to its icy twin, Neptune. On the other hand, if the core is fractured or disrupted, it might hint at catastrophic events that forever altered Uranus' internal dynamics. Even more astonishing is the possibility that Uranus' interior could harbor exotic states of matter. Under the crushing pressures found deep within the planet, scientists theorize that elements like methane may break apart, releasing carbon that could potentially form diamonds. These diamonds, if they exist, might sink toward the core in a dazzling diamond rain, a phenomenon hypothesized but never observed. Such processes, though purely speculative for now, would rewrite our understanding of chemistry under extreme planetary conditions. Yet, the answers remain just out of reach. Without dedicated missions to explore Uranus up close, every hypothesis about its inner workings is built on a foundation of indirect observations and educated guesses. A probe capable of piercing through its thick atmosphere and sending back data from the depths could forever change how we view this icy giant. Until then, Uranus' internal structure remains a tantalizing riddle, holding the echoes of ancient cosmic events and the potential to unveil principles that apply not only to our solar system, but to ice giants light years away. As we close this chapter on the unexplained mysteries of Uranus, one thing becomes clear. This enigmatic planet holds answers to questions we may not even know to ask yet. Beneath its frigid, blue-green surface lies a treasure trove of scientific discovery, waiting for humanity to unlock its secrets. While we've only begun to scratch the surface, the journey to uncover the truth about Uranus promises to deepen our understanding of the universe in ways we can scarcely imagine. The quest continues. What might we discover next in the silent depths of this icy world? Now turning to the prospects of future exploration, the question arises: how can we unlock the enigmatic secrets of Uranus? Despite being one of the most intriguing planets in our solar system, Uranus has been studied up close only once, during the fleeting visit of Voyager 2 in 1986. That brief flyby provided invaluable insights but left us with far more questions than answers. For decades since, Uranus has remained largely overlooked in the realm of planetary exploration. However, recent advancements in technology and a growing interest in understanding ice giants have reignited discussions about dedicated missions to this mysterious world. One of the most ambitious concepts currently on the table is a flagship mission designed specifically for Uranus, including a sophisticated orbiter and a dedicated atmospheric probe. The orbiter would spend years studying the planet, capturing high-resolution images and conducting detailed analyses of its rings, magnetic field, and moons. Meanwhile, the atmospheric probe would plunge deep into Uranus' thick, methane-rich atmosphere, relaying critical information about its temperature, pressure, and chemical composition. Such data could confirm or challenge long-standing theories about the planet's internal structure, atmospheric dynamics, and heat radiation, or lack thereof. But the mission's ambitions would not stop at Uranus itself. Its 27 known moons, especially the larger ones like Titania, Oberon, and Miranda, are equally compelling targets. A spacecraft could investigate their strange surfaces, unique orbits, and potential for subsurface oceans, which might even harbor conditions suitable for microbial life. High-resolution mapping and spectroscopic data could finally reveal how these moons formed and evolved, shedding light on their chaotic and varied histories. Additionally, the probe's ability to study the planet's faint, dusty rings could unravel their composition and origin, distinguishing whether they are remnants of shattered moons or debris from an entirely different process. The implications of these efforts extend beyond Uranus. By better understanding this icy giant, scientists could gain critical insights into the evolution of similar planets in other star systems. Ice giants like Uranus are thought to be among the most common types of planets in the universe, meaning these findings could serve as a blueprint for understanding countless exoplanets. Furthermore, the mission could clarify fundamental questions about magnetic field generation, extreme atmospheric chemistry, and the nature of exotic materials under crushing planetary pressures. While no mission has officially been greenlit yet, growing advocacy among scientists and space agencies worldwide has kept the dream alive. Proposals from organizations like NASA and the European Space Agency suggest a potential launch target within the next 2 decades. This timeline aligns perfectly with Uranus' orbital position, allowing for a more efficient journey and optimal communication with Earth. With advancing technology and stronger international collaboration, the odds of such a mission becoming reality appear more promising than ever. As humanity stands on the verge of a new era of discovery, the prospect of exploring Uranus underscores the boundless curiosity that drives us to reach further into the cosmos. Each question answered by such a mission would not only deepen our understanding of Uranus, but also bring us closer to unraveling the mysteries of the universe at large. So, will we soon take that bold step to uncover the secrets of this icy giant? With the future of space exploration shining brightly, the possibilities seem endless. As we delve into the next chapter of Uranus' narrative, the question of its complex and enigmatic history takes center stage. How did this icy giant, with its extreme tilt and peculiar characteristics, come to exist in its current form? One prominent theory suggests a catastrophic collision in the planet's past, possibly with an Earth-sized object, which could explain its unusual sideways rotation. This hypothetical event may have radically altered its original axis, setting Uranus apart from every other planet in our solar system. Yet, despite its plausibility, no definitive evidence has been uncovered to confirm this scenario. Another puzzle lies in Uranus' apparent migration within the early solar system. Did gravitational interactions with other forming planets push it outward to its current distant orbit, or did it always reside in the cold outer reaches of the solar system? Some simulations imply that Uranus and Neptune may have swapped positions early in their development, a possibility that raises even more questions about their shared origins and divergent paths. If such a migration occurred, what does it reveal about the turbulent environment of the early solar system? Even its moons and rings add layers of mystery to the planet's history. The chaotic orbits and strange compositions of its moons suggest a dramatic and possibly violent formation process. Could these moons have formed from the remnants of past collisions, or were they captured from elsewhere in the solar system? Similarly, the dark, dusty rings of Uranus could hold the key to understanding whether they originated from shattered moons or other debris, and whether they have persisted unchanged or evolved over time. Adding to the intrigue is the role of Uranus' magnetic field in its past. Tilted and offset from the planet's core, the magnetic field hints at an internal structure unlike anything we see on Earth or other planets. Could this unique characteristic be a result of the planet's formation process, or was it shaped by external events like collisions or gravitational influences? This represents yet another piece in the puzzle of Uranus history that scientists are eager to solve. Speculating about Uranus history also forces us to confront the limits of our current knowledge. Without further exploration, many of these questions remain tantalizing mysteries, with only fragments of evidence to guide our understanding. Yet, it is precisely this uncertainty that makes Uranus so compelling a planet that challenges what we think we know and dares us to seek answers. Moving forward, let us explore why uncovering such mysteries is not just an exercise in curiosity, but a critical step toward grasping the broader story of planetary science. As we set our sights on the broader significance of studying Uranus, it becomes clear that this icy giant serves as a gateway to uncovering fundamental truths about planetary science and the evolution of our solar system. Uranus, with its unique characteristics and behaviors, represents a class of planets known as ice giants worlds that are distinct from both the rocky terrestrial planets and the larger gas giants. By unraveling the mysteries of Uranus, we gain insight not only into its own complex nature, but also into the processes that shape the outer planets as a whole. These lessons are vital for understanding how planets form, migrate, and evolve over time, offering clues that extend far beyond our immediate cosmic neighborhood. What makes Uranus particularly fascinating is its potential to act as a stand-in for worlds located light years away. Ice giants like Uranus are believed to be among the most common types of planets in other planetary systems, often detected in the form of distant exoplanets orbiting stars far from our own Sun. Despite their abundance, our understanding of such planets remains limited, and Uranus offers a rare opportunity to study this class of planet up close. By examining its atmosphere, internal structure, and magnetic field, scientists can create models that help interpret data from exoplanets and distant star systems, bridging the gap between theoretical predictions and real-world observations. Additionally, Uranus challenges long-held assumptions about planetary composition and behavior. Its faint heat emission, peculiar rotation, and skewed magnetic field defy traditional expectations and force scientists to rethink the fundamentals of planetary physics. These peculiarities encourage the development of new theories and spark innovation in research methods, leading to advancements that could be applied to understanding other celestial objects. The lessons learned from Uranus may ultimately refine our ability to detect and characterize planets in other star systems, improving our understanding of potentially habitable worlds and the likelihood of finding life beyond Earth. Moreover, any mission to Uranus stands to deepen our grasp of our own solar system's history. By studying its rings, moons, and atmospheric dynamics, we can piece together events from the early days of planetary formation, shedding light on the chaotic processes that gave rise to the planets as we know them. Uranus acts as a time capsule, preserving clues about the conditions and interactions that shape not just itself but the broader architecture of the solar system. In doing so, it enriches our narrative of cosmic evolution, enabling us to trace how our corner of the galaxy came to exist in its current form. In essence, Uranus represents a missing chapter in the story of planetary science, a chapter filled with questions that have the power to reshape what we know about planets and their place in the universe. Investigating this icy giant is not just about solving isolated mysteries. It is about building a more complete picture of planetary evolution, both within our solar system and across the cosmos. As we push forward, the insights gained from Uranus will continue to illuminate pathways for exploration, inspiring future generations to look to the stars with curiosity and determination. As we wrap up our journey through the 25 unexplained mysteries of Uranus, it's clear that this icy giant remains one of the most fascinating and enigmatic worlds in our solar system. From its extreme axial tilt to its faint aurora, peculiar magnetic field, and chaotic moon system, Uranus challenges what we think we know about planets and forces us to push the boundaries of scientific understanding. Each mystery we explored not only deepens our curiosity, but also highlights the immense potential for discovery that lies ahead. This planet is not just a distant, cold world orbiting far from the Sun. It is a treasure trove of unanswered questions that could hold the keys to decoding the secrets of planetary formation, evolution, and even the potential for life in the universe. We live in a time where space exploration is expanding the horizons of what humanity can achieve, and Uranus stands as a robust reminder of how much there is still to learn. Perhaps the most exciting aspect is that every mystery we solve about Uranus can serve as a window into the workings of countless other planets across the galaxy. It connects us to the bigger picture, showing us how our solar system is both unique and yet part of a much larger cosmic story. Whether it's deciphering the origins of its rings, uncovering what lies beneath its icy atmosphere, or speculating about its influence on other celestial bodies, Uranus offers endless opportunities for exploration and understanding. Now it's your turn. What do you think about these mysteries? Are they clues to something even bigger, or do they hint at the unique chaos of our own solar system? We would love to hear your theories and thoughts in the comments below. Together, let's keep the spirit of curiosity alive and growing. If this journey into the unknown has sparked your imagination, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an opportunity to explore the universe with us. The story of Uranus doesn't end here. In fact, it's just beginning. Until next time, stay curious, keep looking up, and never stop wondering about the incredible universe we call home.